Sorry. Some of you may have missed this slide. Okay. But then, how to do this? I'll give you 3 minutes to do it. Just to remind you of the expression. Now, this is easy to remember. If you start with the integration of g df dt, you then end up with fg. Both of them do not have the differential sign. Minus the integration, you will reverse this too. You have f dg dt. That's a minus sign. Note that. Okay. Have you got the answer? So let's do it together. We have something like this. In my mind, this is G and this is df dt. Is that right? So what is F? If the f dt is equal to e to the power minus t, then F is just the integration of e to the power minus t, which give me minus sign, because there's a minus sign here, minus sign e to the power minus t. Is that right? That is F. So I know F. F is this guy. And of course, G is still there. And I have F equal to this guy. So then I have minus sign integration of F, which is this, multiplied by dg dt. My g is just t, so it's dt dt, just that is 1. Is that right? So now I have tg minus t. There's a plus sign, the two minus sign cancel. And I end up with a simple integration of the exponential function, and this gives me a minus sign. Exponential. You go back to the exponential function. So, okay. So one of you show me the answer. Yeah, you are correct. Okay. Now, the difficult thing is that not every integral can be expressed in terms of the elementary functions that we learned. In fact, most integral cannot be expressed in terms of elementary function. So don't expect that you can do every integral. It is simply not possible. In fact, you can do the simplest one. But for the difficult one, you might rely on other methods, or you may do it numerically. Now, if you find that you cannot do an integral, you can find in the integration table. We actually are not using integration table anymore. You can find those big book in the library, but we seldom use that again, okay? Because we are now in the computer era, and people normally use a mathematical software like a Mathematica or MATLAB to do the calculation. You can also have an online calculator. Some of the websites provide an online calculator for doing indefinite integral, and that is available, for example, in Wolfram Alpha. Wolfram Alpha is the same company as that produced Mathematica, a very integrated software that allows you to do symbolic and numerical calculation. And MATLAB is another software that people commonly use, especially by the engineer. Or if you cannot do the integral by whatever means analytically, then you have to resort on numerical method. If you are doing a definite integral, that is of course the simplest way to do it. That is by the numerical method. Okay. I'm not going to teach you the numerical method of doing integration because it's not required in this course. But you can look it up in a book, and it's actually quite simple. You can convert the definite integral into a summation. And if you have a calculator, you can do it very efficiently. These are the basic things about integration and application. You can find it in this website. If you have difficulty with the basic thing, you go to this website and study. Okay. And if you already are very familiar with integration and you want to learn more, for example, you want to learn the numerical methods, you want to learn different methods of integration, you want to find the numerical algorithm, how to derive the numerical algorithm for doing the numerical integration, you go to this extension. Okay. And this part simply introduce to you different methods of doing the integration, and it goes a little bit beyond what I said in lecture. Okay, so that is the important that is a useful reference for you. So we complete the discussion of integration, and then we can formally go to the solving of the differential equation involving kinematics. Okay. Now let's first state the fundamental problems in mechanics. What mechanics is about? What problem we want to solve, and what answer do we expect? That is the important thing. Now, in our discussion, we start with a description of motion. We suppose we know the position of an object at different time, and that gives me the function x as a function of time, right? That is what we start with. And when we do the differentiation, we know the velocity. And when we do the differentiate again on v, we get the acceleration, right? That is what we formulate our understanding of the motion. But in the real life, things do not work like this. Okay, in most of the situation, we do not have a description of the motion. Okay, we do not know the position of the object as a function of time beforehand. So if we know that, there's no problem for us to solve. Okay, so in mechanics, we are actually interested in a reverse problem. What is the reverse problem? The reverse problem is that when an object is affected by force, how we want to ask, how would the body move? That is the problem in the real problem in mechanics. Okay, this problem has sparkled Newton to discover the law of the three laws of motion and also the law of universal gravitation. Now, Newton said that, we will discuss it later, but Newton said that acceleration is actually related to the net force, right? And Newton's second law says that acceleration is simply the net force on the object divided by its mass. That is Newton's second law. So that means if you know about the force acting, the total net force acting on the object, then you know the acceleration, right? Then in principle, we should be able to find the velocity and the displacement a function of time, right? So now this is a diagram schematically illustrating the relationship between the three variables in mechanics: the position or the coordinate x, the velocity of an object, and the acceleration. Now, when we start our course, we start with x as a function of time, and we do a differentiation to find v, and for another differentiation, we turn v into the acceleration a. That is what we discuss in the beginning of our term, right? But in fact, in the following discussion, we will start with the reverse problem. We are given the acceleration, because we know what kind of force is acting on the object. So that means we know the acceleration, and we want to go back. We want to go back to find the position of the object and the velocity of the object. So that is a fundamental task of all mechanics problem. We are given the force and therefore acceleration. And from the acceleration, we want to find the position and the velocity of the object as a function of time. Okay? Now, but you may be tempted to say, if I go from x to v to a, I have two differentiation. Then if I go back from a to v to x, I will reverse the whole process, right? And that involves integration, because integration is a reverse process of differentiation. So if I go from x to v through differentiation, I must be able to go back from v to x by integration. And the same applies for a and v, right? But that is not that simple. It is not that simple because the problem is tricky. In most of the situation, the net force or the acceleration is not given by a function of time. It is usually given as a more complicated function of position and velocity. That is the tricky thing. Now, say, for example, this is a spring mass system. You might have seen this in high school. You have a spring, and you now tie a mass at one end, and so the mass will oscillate in a spring. Now, you can notice that the force on the spring, the force due to the spring on the mass, is a function of the displacement. When the displacement is large, when the spring is stretched by a larger extent, the force on the spring increases. If you stretch a spring and if the spring has a larger extension, then you have a larger force, right? So the force depends on the extension. And the Hooke's law says that the force on the spring, due to the spring, is proportional to its extension. So if I measure this extension by x, then the force of the spring is proportional to x. And that's given by Hooke's law. Okay? I use a constant K here. The constant K is the constant of proportionality. It simply means that if I stretch the spring to a longer length, then it has a larger force. Okay, and the minus sign denotes that the force is in opposite direction to the displacement. If I stretch the spring downwards, then the force will try to pull me back, and so there's a minus sign. So now the force is given as a function of x, the displacement or the position. It's not given as a function of time, right? And there's of course another force, the weight of the object, but that's a constant. That is more easy. But the difficult thing is the force of the spring is not a function of time, but it's a function of displacement. Now for a ball moving in air, for example, a baseball moving in air, it might be subject to air resistance. I call this a drag force. I denote it by F drag. The weight is there, again, simple, but the drag force is difficult. The drag force may be proportional to the velocity or some power of the velocity. And what it means is that when the body is moving fast, it is subjected to larger air resistance. Okay, when the body is moving slowly, air resistance is small. But imagine if the body is moving very fast, then it will be subjected to a larger air resistance. And in general, the drag force may be proportional to some power of the velocity, and is in opposite direction. So I can write the drag force as a constant b with a minus sign, multiplied by v to some power. And in some special case, the proportionality may be simple and simply proportional v for viscous force. But again, you can see the force is proportional to the velocity or some power of the velocity. It is not given as a function of time. Okay. So that result in a very complicated situation. You are given the acceleration because you are given the force. But the force is not simply given as a function of time. There may be a time component, there may be a time dependent, but the force will also be given in terms of the displacement and the velocity, which themselves are a function of time. Okay? The displacement r, the position of the object r, and the velocity of the object, they are unknown function in time, right? Because we haven't solved this problem at the beginning. So the r and v, they are unknown function in time. And the unfortunate thing is that our acceleration is given in terms of this unknown function. Okay, the acceleration is given as a function of r and v, but how do they depend on time? We don't know. Okay, and the acceleration can of course be written as the time derivative of the displacement as a second derivative. So a is d squared r dt squared. Now you can see this equation is very complicated. We don't know r as a function of time, right? And a is given as a function of r, and it's given as a function of velocity. Okay, the dependence is inside, but we don't know that's dependent. Okay, and our task is what? Is to solve for r, because we eventually want to know the position of the object at different time. So that involves solving a so-called differential equation. And that is a difficult task because the dependence is very complicated. And what's r, what's v, we don't know beforehand. So there's no way for you to simply doing the integration to get a result. You have to solve the differential equation. And that differential equation is commonly called the equation of motion. Okay, that is the name that denotes this equation. Okay, so the fundamental problem is that we want to find r as a function of time by solving this so-called differential equation of motion. The equation is difficult to solve in general, and we will only discuss very simple cases. We will only discuss the simplest case in this course. We will not go into the difficult case. And I would say for most of the difficult situation, the equation cannot be solved analytically. and you have to rely on numerical method. You have to rely on the computer. And that's why using computer to do simulation is very important now in physics. Because most of the problem that we encounter involving the equation of motion cannot be solved by analytical function in a closed form. Now, besides solving the differential equation, you also have to impose the initial condition. That means you have to specify where the object is and its initial velocity in order for you to fully specify its later motion. Okay. Now, suppose you throw a pen at a certain position, and you want to predict its position in a second later and its velocity in a second later. You have to solve the equation of motion, but you also have to specify the initial position, initially where it is. You have to specify that. And also you have to specify with what velocity you throw the object. Otherwise, you will not be able to predict its future, right? And those are called initial condition. So in solving the differential equation, you have to impose these initial conditions into the solution in order for you to fully specify, to fully describe the subsequent motion of the object. Okay, so these are the two important things. You have to learn how to solve the equation and to impose the initial conditions. So that is the idea of Newtonian mechanics. You first know the net force, and also, of course, the acceleration. But the net force or the acceleration is given as a function of positional velocity. And so, what you resolve when you equate the acceleration with d square r dt square, you get a differential equation of motion. And after solving the differential equation of motion, you have to impose the initial condition, that is the given initial positional velocity, to fully specify the position of the object. That is a strategy of solving the problem in Newtonian mechanics. Now let's try the simplest problem. The simplest problem is the uniform acceleration. That is what you learn in high school. Okay, you don't learn how to use differential equation to solve it. You just learn it by using a simple graph. You plot a graph of velocity against time, and by looking the area enclosed by the VT graph, you get the displacement, right? You learn those methods. But now we are going to formulate the whole thing in terms of a differential equation and see how this problem can be solved. Now, I know that the acceleration is dv dt. That's right. That is my definition. And now you state that the acceleration is constant. So a is a constant. Okay. It means that it does not change with time. It's always, the acceleration is always that value. And it may take the value of 9.81 meter per second square when you are talking about the problem of falling free under gravity. Okay. So what we are going to do, we simply integrate both sides. Okay. We want to cancel the differentiation in order to get the velocity, right? So that means we want to cancel that by doing integration on both sides. So we may write, for example, we may use the differential notation. We might put the dt on the right-hand side, and we integrate both sides. And in doing the integration, we have an integration constant. Somebody like to put it in along this line, but somebody may like to put it on the last line. Depends on your choice. That doesn't matter. Now, when I integrate both sides, what we get? What do I get? The left-hand side simply give me v. The right-hand side, I integrate a constant. The constant is a number, right? So integrating a constant is just I just put it out. And integrating dt is just t, right? So I guess v equal to at, but do not forget, I'm doing indefinite integral. So that means I have an undetermined constant. And that undetermined constant is the integration constant, c. Okay. Now, I must give you a warning. that integrating dA dt equal to AT is possible only when A is a constant. In this case, we assume a uniform acceleration, meaning that A simply is a number. And in that case, I can do that. Okay. But imagine if A is given as a complicated function of velocity and position, you can't simply do that integration. And solving that differential equation will be difficult. Okay. So I give you a warning, don't do it wrong in the examination. You can't do, you can't go from integration ADT to AT in general. If A is not is a function of time, it's a function of V and R, then you cannot do this. Okay. Now, so we got this formula. What this formula means is that the velocity at the latter time t is given by AT plus a constant. That is what this equation means. Okay. Now, but we have to specify the initial condition. How do we do that? We know that the object is initially moving with a velocity u. That means at time 0, when we put t equal to 0 in this equation, the velocity of the object should be equal to this initial velocity, right? Because we know the object starts with a velocity u, right? So when we put time t equal to 0, the velocity v must be equal to its initial velocity, which we denote by u. And so when t is 0, with this time is 0, v is equal to u, and that means u is equal to c. And so we got a constant. The constant is u. Okay. And eventually, when we put the c back, when we replace the c with a u, we got v equal to u plus at. Well, this is what? This is the simplest uniform accelerated simplest equation for the uniform accelerated motion. V equal to u plus at. You learned in high school, right? Now we do another integration. Suppose v is dx dt. Okay. The velocity is just a time derivative of the position, right? And so dx dt is equal to u plus at. Again, I can move the dt to the left-hand side, to the right-hand side, sorry, and I do the integration on both sides. Okay. The left-hand side simply gives me x. Okay. The right-hand side, integrating u, a constant, will give me ut. The constant a can be put out, and integrating t will give me t squared over 2. So I now have the second term as half at squared. And do not forget, because I'm doing an indefinite integral, I have an integration constant I call c prime. Now, every time when you do an integration, you always involve an integration constant. And it is that integration constant that allows you to input the initial condition. Now, in this integration, we have a constant c. So we input the initial velocity u. And now for the displacement, you have another integration constant, which we call c prime. And that exactly allows you to input the initial position of the object. Okay. So what is this initial position? The simplest choice of the initial position is that at time 0, the particles start from the point x equal to 0. And if I put t equal to 0 on the right-hand side, and I also put x equal to 0, I get c prime equal to 0. So c prime has gone, and I got x equal to ut plus half at squared. What is this? This is the equation, another equation of motion you learned in high school on uniform accelerated motion, right? I can also, if I like, I can also eliminate a t, because I know v is equal to u plus at. So I can make at the subject of the formula. I can write t as v minus u over a, and I substitute it into the expression of x. So xb will become, I extract a factor of t first. So I replace the t with v minus u over a here. I also replace this t inside the bracket by v over u minus a over a, and a cancel with this. And after some algebraic manipulation, I find that this bracket is equal to v plus u So v plus u multiplied by v minus u is v squared minus u squared. And I divide by 2a. And rearranging, we get v squared minus u squared equal to 2ax. And this is again, of course, another equation of uniform accelerated motion. And these three equations are the motion equation you learned in high school. Okay. Now we only have studied a special case, that is a uniform accelerated motion. When we start with a displacement x as a function of t, in our discussion, in our first discussion, we say if we find the derivative of x, then we are equivalent in finding the slope of the curve, and we have and that is the velocity. The slope of the curve is the velocity. So by doing a differentiation, we go from the displacement to the velocity. And for the case of uniform accelerated motion, the velocity is a straight line. It's linearly increasing with t, v equal to u plus at. But we can find the slope of the velocity curve again. And the slope of the velocity curve will give me the acceleration. And in the case of the uniform accelerated motion, the acceleration is a constant and it's given by a horizontal line in the AT graph. Okay. So in going from x to v to a, we do differentiation. Okay. But you can also go back. If you are given a constant acceleration and you calculate the area by doing integration of a, you got a velocity. You got a velocity as a function of time. And if you find the area bounded below by the velocity graph, you do an integration of v, you go back to the displacement x. Okay, so by doing successive integration, you go back from a to v to x. Okay, now of course the graph I show here is for a uniform accelerated motion in which a is a constant. But the relationship between a, v, and x, they are general. They are general. Okay. In particular, when you go from x to v to a, you need to do a differentiation. And if you want to go back from a to v to x, you are doing effectively you are doing integration. Okay. Now, let us use what we learned to solve a 2D problem, and that's a projectile motion. Now, this is the setting of a projectile motion. I've shown you before. The only acceleration is the downward gravity. So I denote it by minus gj, okay, in this coordinate system. J is the vertical axis, so the direction is downward, so the direction of the acceleration is minus j. The magnitude of the acceleration is g equal to 9.81 meter per second squared. Okay. So the equation of motion, now a vector equation, is dv dt equal to minus gj. Okay. J, the only acceleration is the downward gravity. Okay. So now I integrate this over t. Okay. I just integrate both sides. Okay. And the left hand side gives me the velocity. I integrate a constant, even though it has a vector sign, it's still a constant, right? G is a constant, J is a constant. So I simply have a t here. And do not forget, I have an integration constant. So I have an integration constant c, but that is a vector because this is a vector equation. Okay, so c, the integration constant, is now a vector. Okay, now I input the initial condition. The initial condition is such that at time 0, where this term vanishes, the velocity v is equal to the initial velocity u. The initial velocity u is like this. Okay, it's at an angle. It's described by the vector u. So that means my u is actually equal to c. And so now I have the velocity equal to u minus gtj. Okay. And of course, I can write my velocity in terms of the derivative of the displacement vector, or of the position vector. So v is dr dt, and I found that it is equal to u minus gtj. So now I have another differential equation. And by integrating once more, I should be able to get R, the position of the object at different time. So I now do another integration. Okay, I start from this and I integrate both sides. Of course, the left-hand side gives me the R, the position of the object. The right-hand side, I start with U, I do the integration, I get UT, because U is a constant anyway. And in the second term, I have minus GT, and I integrate the T, it gives me minus T, 1/2 T squared. So now I have minus 1/2 GT squared, goes with the vector J. And of course, I have another integration constant I call C prime. And if I start my motion from the origin, and that means when T is 0, these two terms vanish, R is also 0, and that means the C prime, that constant, is also equal to 0. So I get rid of that constant. And I have this expression as my position of the object as a function of time. Now you can easily go back to the components. If I look at this equation, this is a velocity v. Okay, v is equal to u vector minus gtj. If I take the x component, the j is the y component. So if I take the x component of this equation, it does not involve the j. And the velocity x component of velocity is simply vx. The x component of the initial velocity is simply ux. So we have vx equal to ux. And if we take the y component, this becomes vy, this becomes uy, and the y component of the j is of course minus gt. So we have the equation for the y component of the velocity. Okay. And how about the displacement? For the displacement, we have this equation, right? If we take the x component of r, we get x. If we take the x component of u, we get ux, right? The j component doesn't enter because we are talking about the x component. So we do not have the j, the g here in the x component of the motion. How about taking the y component? This becomes y, the y component for the displacement. This becomes uy, right? And the j component, of course, gives me a term of minus half gt squared for the j direction, for the y direction. So now we exactly reproduce our result learned in high school. These are the equation of a projectile motion under uniform gravity. Now, so let's stop here, okay? In the